Greetings to you. My name is Andrej Sepcic, and I'm going to be your presenter today. So let us start. What is tan delta and why do we measure it? So tan delta is, as we said, the most common technique used to assess the insulation of primary equipment like medium and high voltage transformers, but also current and voltage transformers, rotary machines like generators and motors, also cables, medium high voltage cables, circuit breakers, surge arresters, all type of primary equipment. Let us say anything that has an insulation can be tested using this method. It is important to emphasize also that this is an AC test. It is not a DC test. An AC test means, of course, that we will not be using a direct current or direct voltage. We will be using alternate voltage and alternate current. Of course, there are different methods, but today we will be focusing on an AC test. And this test is used to check aging of insulation and also mechanical deformation. So this is just in short what you might expect from this, this session today. And what we will do is we will actually, let's say, do a kind of easy introduction to what we will be talking about today. Since we talk about insulation, we know that today we have all types of insulation. We have thermal insulation, which you will use to insulate your house. We talk about sound insulation, which will be used, for example, in a studio when recording. But today we will talk about electrical insulation, and we will be mostly focusing on transformers. Of course, as I said, it can be applied to many other assets, but due to the fact that the transformers are a very good thing to take as an example when talking about tan delta, we will be focusing on transformers, and in that we will be focusing on power transformers. Today, when we talk about insulation, so we have few types of insulation. We have a solid insulation, liquid insulation, and gaseous insulation. So solid would be cellulose, which is paper and pressboard, which is something which you will often find in a power transformer. For example, you can find it in a while you wrapping the primary or the secondary winding. You can also we can also use cast resin as a type of solid insulation, and we can also use porcelain, which is very often used, for example, for bushings and similar, let's say, current and voltage transformers. Apart from that, we also have the chance to use liquid insulation like mineral oils, silicone oil, which is more expensive than the mineral oil, and all types of synthetic compounds, which are usually used with power transformers to insulate and also cool down the transformer, the windings, the core, etc. And then we have gaseous insulation, and the gaseous insulation is something which, for example, very often sulfur hexafluoride or electrogas is often used since the 30s, 1930s, air and vacuum, or nitrogen. So obviously these are all compounds, elements which are electrically inert, which don't conduct electricity. And when we talk about insulation, let us define it. If we want to talk about it, it's a good idea if we can define it. So we are defining the insulation as a material or a combination of materials, suitable non-conductive materials that provide electrical insulation of two parts at different voltages. So it's a very straightforward and quite understandable definition, but still let us focus on one element. Let us focus on the fact that material or a combination of suitable non-conducting materials. So what do we mean by this? Well, obviously, we can have only one material as an insulator. For example, it can be just a cast resin in a dry type transformer, or it can be porcelain in a bushing. But very often in a power transformer we will have a mix. We will have a mineral oil and the paper, or a mineral oil and paper and the press board. So this is important because later we will refer to this definition and see why tan delta is so good, and I'll just give you a hint. It's good because it doesn't measure the insulating properties of only one material in this set of materials. It gives us an idea about the whole insulating system which we have installed. Now, I hope we have clarified this. The next thing which we will talk about is the end of the definition, which says two parts at different voltages. So two parts at different voltages is, let us put it like this. If we have two different voltages, each on one side, and we have a dielectric or an insulator in between, does this sound familiar to you? Well, I hope it does, because it is a definition of a capacitor. And this is important because since we will going to model today the insulation as a capacitor, let us take a look at what is actually a capacitor. So all of us have an idea or maybe know very exactly what a capacitor is, but capacitor exactly is two conductive plates with a dielectric in between them. The capacitor has a certain area or the size, and there is a distance between two plates, and actually the characteristic of a capacitor is to store electrical charge. Now, why am I saying this? Well, I'm saying this because when the transformer, for example, was being built, even though the idea that there will be some capacitance, let us call it just for now a parasitic capacitance, will appear, it is there. It is a physical reality of any transformer, because you can say that this is, for example, a high voltage winding and this is a low voltage winding. In between, you have some paper and some oil which constitute a dielectric, which in turn, whether we want it or not, constitutes a capacitor. So we could say that we can easily model an insulation as a capacitor. Or maybe it's not high and low voltage side on the transformer, maybe it's a high voltage and ground, or maybe low voltage and ground on some of the primary equipment. So whenever we have two different electrical potentials and the dielectric in between, we have a capacitor, something that can hold an electrical charge. Even if we have an overhead line, which is running above us, there is a parasitic capacitance between that line and the ground. Of course, it's a very small capacitance because the distance is very big, but it's there. And since it's there, let us use that to understand what is the state of our insulation. But in order to do that, we need to dig a little bit deeper. We need to see the basic formula for a two-plate capacitor. So we can see here that we have a capacitance, we have a permeativity, the area, and the distance. So the bigger the area and the bigger the permeativity, and the smaller the distance between the plates, more electrons I can store inside. And this is the core of understanding tan delta, because first of all, the permeativity is one thing which can change, of course, and it can change if, for example, the properties of our insulation changes. If our oil gets too much water molecules inside, the epsilon will change. Also, if there was an earthquake, heaven forbid, and the two plates or two windings have become more closer, then these two parameters will change. So we can have a permittivity which would constitute a problem with our insulation, or we can have A and D changing, which in turn would mean something else. It could mean that something physically moved inside, or maybe all of them can change. Maybe we have bad insulation due to the, let's say, gases inside, and something physically moved, so that's why the capacitance changed. So if the transformer was produced in a factory, and then the initial measurement was done, and we got, let's say, 5 nanofarad, and 5 years later we measure again the capacity, the parasitic capacitance as we called it, and we get not 5 but 7 nanofarad, then we know that there is quite a lot of change inside of our transformer. Actually, it could be insulation, or it could be something else. It could be physical movement which happened inside. But moving on, let us talk about our capacitor. Now, in a capacitor, we all know that current and voltage are shifted in phase by 90 degrees, which means actually first you have a current, something flowing in, and then the voltage builds up. And it's always 90 degrees. So the current is leading and the voltage is lagging, as you can see here. That is because the ideal capacitor has no in-phase current. It doesn't have any resistive current, and it doesn't have any resisting current because it's an ideal capacitor. But you might already understand that since there is no such a thing as an ideal capacitor, we will introduce the concept of a real capacitor. And a real capacitor differs from an ideal capacitor by the fact that there is not 90 degrees phase shift between current and voltage. It is less than 90 degrees. So later on you will see actually that the tan delta is actually quantifying the difference between ideal and the real capacitor. So what is this real capacitor? Well, the real capacitor itself has one resistor connected in parallel. This resistor has a huge resistance. We talk about hundreds of megaohms, which means that the current flowing through this resistor is very small, in the range of milliohms or milliamps or microamps, but it's not zero. And if it were zero, then we wouldn't have all this webinar today. We wouldn't have any issues actually with the insulation. It would be perfect. But since it's not zero, what happens is that the current running through this resistor creates some issues. So another way how we can explain this is that there is no material on the face of the planet or in the universe which has infinite resistance. Every piece of material, even if it's a dry wood, has a finite resistance. If you take 2 meters of dry wood, completely dried out, and connect 100 kilovolts on the two sides, there will be a current running through that insulator. It will be a small current, but there will be a current. So there will always be some resistive current going through this resistor, and let us see how we can use that while modeling the insulation. So here we have our real capacitors used on a PCB, and we can say that we are actually searching for the values of insulation's equivalent scheme. So since we can model our insulation as resistance and capacitance connected in parallel, we actually are searching for resistance and capacitance, and tan delta is a physical reality that somehow connects these two elements. So by measuring resistance and capacitance, we measure tan delta. This is also the answer to the question why, when we measure tan delta, we often get a result. As a result, we also get the capacitance. It is because of this. We also get this result. We might not, let's say, pay too much attention to it, but it is there. And how do we do that? Well, we do that by generating voltage and by measuring the current through the equivalent capacitance and equivalent resistance. We actually cannot measure directly this current and this current. We measure this total current with an ammeter, of course not like this one, something better, but we do measure the phase shift between the voltage which caused this current and the current which was caused by that voltage. So, of course, we will be more interested in the resistive current. Why? Well, we are more interested in the resistive current because the resistive current is in phase with voltage, and the resistive current, if we look at this formula, has cosinus phi 1, which means that the power which is dissipated on our insulation actually is voltage times current. Now let us take one example. Let's say that we have a 10 kilovolt transformer, and if we if we have a 10 kilovolt transformer, let's say on the primary side, and only 1 milliamp of resistive current, so it's 1,000th of an amp, the power which is dissipated is 10 watt. 10 watt per se is not a big power. I mean, light bulbs used to be, and the light bulbs with filaments are between, let's say, 30 and 100 watts. But 10 watt for 1 hour will dissipate 36,000 joules or 10 watt hours on the insulation of that transformer. Also, if that lasts for the whole day, we will dissipate 240 watt hours, in a month 7.2 kilowatt hours, and in a year 86.4 kilowatt hours. If we take in the mean value, price of 1 kilowatt hour, we will lose about 15 euros per year on a small distribution transformer. But it's not the funds, it's not the money which is important here. It is the fact that all this power turns into heat. And that heat is what is problematic. That heat is problematic because the heat has a detrimental effect on the insulation. Let's say if you drive a car, every car has a cooling system. Because as we know, the Carnot process explains that ideally we can maybe transfer about 36% of all the energy which is in 1 liter of gasoline, into kinetic energy of a car, into movement of the car. Realistically today, if that is 20%, it is great. But what about the rest 80%? It is heat which is generated. And that heat which is generated needs to be removed. Because if it's not removed, then we will have an issue, we will have a too high temperature, and we will not be able to operate our machinery. So if you're not sure if what I'm saying is true, try to break down the cooling system in your car and see how far you will get. So the reason why the resistive current is a problem is that resistive current dissipates a lot of heat, and the heat can easily destroy our insulation. It can lead to something like this. And because we don't want something like this happening, what we want to do is we want to keep under control the state of our insulation. So with the heat being applied constantly on the insulator, the insulation starts to degrade, and which as a consequence has an increase of the resistive current. As the resistive current increases, more heat is dissipated. More heat in return additionally degrades the insulation, which now allows more resistive current to flow, and it goes on and on and on, and it's a vicious circle. It's a chain reaction which, if not stopped at the right moment, will cause something like this. So hopefully that will not happen. And let me tell you a story. You see, we talk about insulation today. And one aspect of insulation are also dikes. Not the one on bikes, but the dikes in Netherlands. This is one dike in Netherlands, and it is used to insulate the sea from the place where the people live or graze their cattle. You can see that the level of this sea is higher than this level here, so this is a depression, and if this dike were to sprung a leak, it would be an issue. So there is this story about a young boy called Hans Brinker. It's a Dutch legend because, as we said, the dikes in Netherlands are essential to insulate people from the sea. Now, this boy, Hans, was coming back from the visit to his sick grandfather, and while returning, he saw a leak in a dike. All kids, as well as the grown-ups in Netherlands, know that if you see a leaking dike, you should put a plug. You should plug that hole, and you should do it fast. And you should do it because if there is the smallest visible leak, nobody knows what's happening inside the dike. You cannot jump inside and see what's happening, but this one small leak can easily create havoc. So imagine like if you have a dam which is also a type of an insulation. Here you have water, here you don't. But if the leak would sprung, for example, here, just 5 or 10 centimeter in diameter leak, that leak, it wouldn't take long for that leak to break down the whole barrier, the whole dam, because this is a very non-linear process. You see, and because of that, what the Hans, in this case, did, he actually plugged that hole with his finger. He plugged that hole good, and he shouted whole night calling for help. Only in the morning, the priest who was passing by on his bicycle saw him, and Hans was exhausted because he was cold, he was shouting all night. So the priest called the villagers, which relieved Hans of his duty. And that's how he became the boy who saved the village. Now, tan delta is not Hans Brinker. We cannot, unfortunately, plug the hole. But what we can do with tan delta is we can understand how big the hole is, let's say metaphorically. It helps us to understand how functional or how deteriorated is our insulation. So the story does inform us about the non-linear process of the insulation deterioration, because a small hole, only a few centimeters in diameter in a dike, can very quickly destroy the whole dike. The same way, a small resistive current can cause an insulation deterioration and a short circuit in a power transformer, because we all know that in a power transformer, all distances are very small and have even smaller margins. Well, another way how to see this is imagine what happened to me. Actually, this is a true story. I was in an exhibition, and I saw on one stand a fish tank. It was filled with what I supposed was water, but inside there was a TV set. Inside the fish tank there was a TV set. And the guy who was on the stand was changing the channels and watching the television, which was immersed in an aquarium which had no fishes, but it had a transparent liquid inside. Well, that transparent liquid inside was mineral oil. And because the mineral oil is an insulator, the TV functioned properly. There was absolutely no problem with insulation, and the TV was functioning okay. But now imagine that you have this situation back home, and every day you put 1 drop of water inside that tank, and then you stir it up. After 5 or 10 days, probably nothing would happen. Maybe nothing would happen after 50 days. But if for 100 consecutive days you would be putting 1 drop of water inside and stirring, at one point in time what would happen is that there would be enough water inside that mineral oil to cause a short circuit. And that's what happens, that is what happens inside of your power transformer. You have a transformer which breathes, we'll talk about that later. That transformer attracts water molecules inside, and the water molecules sooner or later can create a short circuit. So what we do here with tan delta, we will measure and tell you when is the high time to get your TV out. And finally, to answer the question why we test tan delta, we test tan delta because we want to know the state of our insulation, or we want to know how far are we from the insulation breaking. And since insulation has a very nonlinear characteristic, a very small increase in resistive current can suddenly make the insulation break. So also it's important to emphasize that the high value of tan delta, not too high, and later you will find out what is high, is not necessarily a sign that we need to change the asset. Often what we need to do is simply to follow the trend. And by following the trend, we will also know, do we need to change that asset or not? So another way to answer the question why we do a tan delta test, we do a tan delta test to keep our asset running.